Today I'm going to derive the Schrodinger wave equation. It's time independent Schrodinger wave equation. So we just need some basic formulas for that. So we know that the total energy TE equal to the kinetic energy plus the potential energy. We know from the basic formula, we know that the kinetic energy is half mv square plus the potential energy, just considering it's a capital V, it's a small v. Okay, just don't get confused. Okay, total energy is half mv square plus v. So we know that the momentum P equal to m into v. This v is the velocity, not the potential here. So we just need the small v equal to P by m. We just need to substitute in this equation. We get the kinetic energy equal to half m into p square by m square. So we get the kinetic energy equal to p square by 2m. It's a very important equation. So we get the total energy equal to p square by 2m plus the potential V. This equation is important. So we just need to represent a wave. So to represent a wave, theoretically, we just need a function to describe a wave. So we are using a function of the wave. Or we don't know the wave, but we know the function of the wave. We just represent it as the psi. Psi is the wave function. Wave function. It's called as psi. So for deriving for the wave, we are considering a wave. I'm writing psi equal to cos kx minus omega t plus I sine kx minus omega t. From our basic mathematics by trigonometry, we know that the de Moivre's theorem, it gives a result. We know that cos theta plus I sine theta equal to e raised to e to the power I theta. The e to the power I theta, it's the polar form. So we just need the polar form here. Here the theta is represented as the kx minus omega t. Kx minus omega t. So we can rewrite this equation. So we get of psi equal to cos kx minus omega t plus I sine kx minus omega t equal to e raised to I to the power kx minus omega t. So we can write psi equal to e raised to I kx minus omega t. This is the way which we are considering. To derive the equation, we just need some more basic formulas, some basic formulas. First, for a wave to travel in space, it's need a propagation constant. It is constant for a particular wave. We just need k. The k is called the propagation constant. You can write k equal to 2 pi by lambda. Lambda is the wavelength. And by de Broglie wavelength, we know that the famous equation, lambda equal to h by p. So we know that h bar, it's a constant called h bar. It's it's h by 2 pi. We can write h bar as h by 2 pi. It's a constant value. So, and we know, we just rearrange this equation, we get 2 pi equal to h by h bar. And we know that k equal to 2 pi by lambda. So we just substituting this value in for 2 pi here. In this equation, we get k equal to h by h bar into 1 by lambda. From the de Broglie's wavelength, from the relation, we know that 1 by lambda equal to h by p. So 1 by lambda equal to p by h. This implies, okay, p by h. So we can write k equal to h by h bar into p by h. So solving, this h and h get cancelled. So k p by h bar. So k equal to p by h bar. It's p by h bar. Now we are again considering the wave function psi equal to e to the power I kx minus omega t. And as this, we are going to derive the time independent Schrodinger equation. We are differentiating with respect to x, not with time. So we just need to take the derivative of this function with respect to x. So d phi by dx equal to I kx, the derivative of kx, k, into e raised to I into kx minus omega t. So we know that the e to the power I kx minus omega t is psi. So we can write d psi by dx equal to I k psi. So again, we are differentiating this equation with respect to x. Again, second derivative. So we get d squared psi by dx squared equal to I square k square e raised to I kx minus omega t. We know that e raised to I kx minus omega t is psi. So we just write d squared psi by dx squared equal to I square k square psi. So let's come back to the basic mathematics. I is a complex function, so a complex number. It is root of -1. It's an imaginary number, so I square equal to -1. I square equal to -1. And k, we derived the equation about p by h bar, so we just write k square equal to p by h bar the whole squared. So we just rewrite the equation. We just substituting these two values in this equation. We get d square. We just write here d squared psi by dx squared equal to -1 into p squared by h bar squared into psi. Okay, so we just rewriting the equation. We get we just multiply that equation by a minus. We get d squared psi by minus d squared psi by dx squared equal to p squared by h bar squared into psi. Okay. We just need to rearrange this equation. We are almost there. Okay, just transposing this h bar squared to the left hand side, we get minus h bar squared into d squared psi by dx squared equal to p squared psi. So we know we earlier derived that E, the total energy, equal to the kinetic energy p squared by 2m plus v. So just multiply this equation by a psi. We get, to reach the time independent Schrodinger equation, we just assume we just multiply the psi in this equation. We get E psi equal to, throughout this equation, p squared psi by 2m plus v psi. Okay, so and then we just substitute the p squared psi value in here. We get we just rearrange the p squared psi value here. So we need to just arrange in here. Okay, so E psi equal to minus h bar squared by 2m into d squared psi by dx squared plus v psi. So this is the time independent Schrodinger equation, or just like TESE. So this is the part 1 for Schrodinger equation. So next part will come soon. Thank you for watching. Thank you.